So we've seen how the Earth observation technology can be used to look at patterns of weather and climate around the planet. But my favourite part are the polar regions, and we're very lucky because we've got several different classes of Earth observation sensor which we can use to study those parts of the planet. The oldest class are satellite altimeters. It just measures the shape of the ice and how that changes as a function of time. An altimeter was first designed to look at the global oceans and how they're changing over time. It tells us things like the rate of sea level rise, or more importantly for operational purposes, things like how big the waves are in the oceans, and that's really important for people to know who sail ships around the planet. But we've managed to use the sensors that have been around since the late 1970s to look at the polar ice sheets. So we have a really long record now of how Antarctica, parts of Antarctica and Greenland are changing over time. We also have quite a sophisticated technique to measure the speed of ice from space. Really fine detail can be had by performing interferometric synthetic aperture radar. This technique is used traditionally to look at earthquakes and volcanoes, solid earth deformation, but we can use it to study the speed of ice as well. And that's really important. 20 or 30 years ago, maybe not even as long as that, people didn't realise that the ice sheets changed the speed at which they flowed over time. People thought that the ice sheets had been flowing at the same speed for the past 10,000 years, but that's not the case. We see from the satellite measurements that we've collected from the past 10 or 20 years that actually Greenland and Antarctica change their speed quite frequently, in summer in some places, but also increasing over time in other places. The most recent and most technologically advanced sensors we have now are gravimeters in space, and they weigh the Earth as they fly around in tandem orbits around the planet, and they measure changes in the mass of the Earth as it moves around the planet. And there are two main things that change in the planet. There's the hydrological cycle, the water that moves from the equators to the poles through the atmosphere and then lands on the land or on the ice sheets as snow and transports its way back through to the oceans again. But also the mantle within the Earth itself. And that moves around, sometimes in response to changes in the loading that the oceans and the atmospheres place on the Earth as well. And if we weigh the Earth as the satellite flies around, it can tell us something about how ice is changing in the polar regions. And that's been a really powerful tool for us. It gives us a real definite estimate of how much mass there is in Antarctica and how that's changed. And that's important for sea level rise. Even though we've managed to make great use of the conventional radar altimeters that have been looking at the planet's oceans over the past 20-30 years to look at the polar regions, what we really need is a satellite that's capable of surveying all of the ice that's at the poles. And we now have that thanks to ESA, because they launched Cryosat 2 in 2010. And it's the first European mission dedicated to looking at the polar ice sheets. And we're seeing here the launch from a silo in Russia on a decommissioned and recommissioned intercontinental ballistic missile. And that's the way we send satellites into space quite often these days, because those former missiles are very good vehicles to get heavy loads into orbit. And in fact, Cryosat 2 was launched to within a few kilometres of its nominal orbit, and so it was a fantastic success. The satellite's now in space and has been collecting measurements over Antarctica and Greenland for the past 4 years, and has given us the first glimpse of how the complete polar ice sheets are changing over time, and we've had some remarkable discoveries thanks to the mission. Some of the things that Cryosat does is allows us to look at the shape of the polar ice sheets in much more detail than we've seen before. And this little animation here is going to show how we're able to do that. It's panning around the planet to look at the Greenland ice sheet, and it's going to show some of the data, the first data collected by Cryosat, which allowed us to map the shape of the ice sheet and how it is today. This is really important because we can compare the shape of the ice sheet today to how it was measured 10 or 20 years ago, and we can make an estimate of how much ice is there compared to 10 or 20 years ago. And what we can see here is very fine definition in the shape of the ice sheet, in the rough terrain areas around the edges. You can see this, really steep mountainous areas around the margins of the Greenland ice sheet, which we just couldn't survey before with satellites that were designed to look at really flat, open oceans. Cryosat can tell us a great deal more about the ice sheets than we knew before, and that's allowed us to make some really strong discoveries. If we strip away the ice sheet, you can see the very mountainous terrain around the coast of Greenland, and it's everywhere around the coastline. And that's been a really problem area for past satellite missions, because the mountains just can't be surveyed with the coarse footprint altimeter, maybe 10 kilometres wide. But Cryosat can see these areas, and it turns out that this is where the ice sheet is changing the most. So if we took a band around the edge of the Greenland ice sheet, maybe 50 kilometres wide, all of the ice that's been lost from Greenland today would be in that part of the ice sheet. The ice sheet is melting and flowing too quickly, really close to the ocean. And we couldn't see that before with the altimeters because they were just not designed to do that. We can see it now, and we can track how that part of the planet is changing over time and into the future.